Hello everyone. In this video, we're going to start taking a look at how we can use geometry nodes to customize our normals. Usually when working with custom normals, no extra setup is required to use them in the material. They simply overwrite the base normals of the mesh, which is often quite inconvenient because you can't have both your custom and your base. In geometry nodes, we have to do a lot more work to get our normals from the mesh, put them in the right format, do any splitting we want, and then send them to the material and have the proper node set up to bring them in and not distort them or anything. So we have to do a lot more work, but we have the advantage of being able to edit or customize our normals at any stage of that pipeline. We're going to start with a quick overview of the geometry node group and what it's doing, and the material node group. That will be aimed at giving the broad strokes, and if you're somebody who's already worked with these and is familiar with all these concepts down here, then you'll probably just be able to watch that and skip the rest of it. And the rest of it will be a step-by-step walkthrough of building those groups, going over every single input, what it means, why it matters, and all that. Before we go any further though, take a quick look and see if I put any updates at the top of the video's description. Geometry Nodes is still very new. There's a bunch of things it doesn't support yet, and we're going to be working around some of those limitations. But it's possible that by the time you're watching this, it will support them, especially since some of them are already in the nightly builds for Blender 3.2. So I'll put a note there, or perhaps a link to an article, or I may even do a whole new video if something completely overrides what's here. Although I'm sure that almost all the information in this video will still be useful for understanding how things work, even if we have a slightly more convenient setup in the future. Okay, let's take a look at what we're going to be building. Here is some test objects, our faithful head, Suzanne, and a cube. On these, we've got some sharp edges marked, and we have a subsurf and then geometry nodes group. It's the same group on every object. The normals are based on a generic or anonymous attribute. We've got GNNormals, which is a face corner vector on each of these meshes. The geometry nodes group outputs to it, and then in the shader, we bring it in via an attribute node. Then in this group, we do some minor fixes. It needs to be normalized and inverted on backfaces to behave properly. That's the essential part. The rest of these nodes are just for looking at the normals in different ways or comparing them. For example, we've got my favorite XYZ absolute stepped, so we can really see what we're doing. And it lets us see why this group is so important. If we disable it, a lot of our curvature is missing, especially on this lower poly shape. And we get that back thanks to the Normalize node. We've also got this mix node based on object info, the index, mixing back to the original normals. And that's because I have this instanced copy of the same objects so that we can compare different settings if we want to be able to see it at the same time. And we've got toon shading, of course, and subsurf. So, just the usual things you would want when trying to develop something and see what it looks like. Here's the geometry nodes themselves. Our setup supports having split edges mimicking sharp, but because geometry nodes doesn't support sharp as an attribute, we use a vertex group instead. We also have split angle, which mimics the angle setting under Autosmooth, which of course does nothing since we're using a generic attribute and not even using the real normals. The basic idea of the setup is that we take the geometry, we split it based on either our split group or the angle, then we capture the normals, which are face data, as point data in order to smooth them. That gives us interpolated smooth shading. And then we transfer them as face corners back to the original mesh so that it doesn't remain split. The output for the normals is face corners, which is very important. Most of the setup is pretty straightforward. The core of it is really just capturing the normals as point to interpolate them, and then outputting as face corner to preserve any splits. If you don't split any normals, you can just output them as point, and you can just plug this directly into the output and even skip the capture node. There is some subtlety to the splitting setup. Since our sharp group is a vertex group, it's point data. So we capture it as a Boolean to use it in split edges, and that is going to get anything that has a value above 0 as true. So with this equal, we make it so it's only things with values equal to 1. And that stops subsurf from messing it up when it averages and the weights on the new edges. And for the check edge angle, we add a small value to it to avoid floating point issues and also caused by use limit surface. So technically, our angle right now is 90.01. But yeah, that's about it. You could use different methods of splitting. You could use crease. You could use some other thing. This is just examples of how you can set these up. So yeah, if you understood everything I just said, you can probably skip the rest, although I'm sure you'll still learn something. And if you didn't understand that, well, that's what the rest of the video is about. So enjoy. Oh, and I will be posting this file, including the examples that we'll be getting into. It will be free, but you're welcome to leave a donation. And of course, you can also support me on Patreon. And a big thank you to all the people who have joined recently from the previous videos. Alright, so what exactly are geometry nodes? Well, they are a modifier. We add geometry nodes in our modifier stack, and it obeys all the usual rules of order of operations in the stack. And then we've also got our geometry nodes node editor here. And as soon as I add this, it has created a new node graph. And if this looks familiar, that's because geometry nodes are also node groups. It's not just an editor space that you can put groups within, like that's how shaders work. Every geometry node's graph here is all node groups. Like you can see all my different groups here, which also show up under the groups menu. I've got tons of stuff from experiments. And those show up here. So this new one we've made, we'll call it test 1. That is the group we've assigned to this modifier, and it is also a group in the group list. Well, I think it won't show up here because you can't add a group within itself. But if I made another one, now I can go find test 1. And this isn't really something that matters for what we'll be doing with this, but I'm just telling you to avoid confusion, because some groups don't really work as a modifier. They only work within groups that are the modifier. And that's because if I do something like add a bunch of inputs, like say, we'll get a normal input, output, and then we can also make that into an input here, and they're showing up on our list. And we can see those appearing under our inputs and outputs, and that's all fine. But if we want to do something like make another geometry output, then we start to have an error. And that is because it assumes when you're using it in the modifier stack that the geometry of the object you put the modifier on is going to be the input geometry. So it won't let you use multiple geometry inputs in that case. But if we take this and use that as a group within another graph, then there's no problem if we wanted to have multiple geometries. And we can stick the same group on multiple objects. So I've called this normals 1, and we'll go ahead and stick that on both of these. I'm going to work on it here and pin it so that it doesn't change if I deselect it. And well, we've got our geometry coming in and going out. And if we stop it going out, well, then we've got nothing. Now, as we do this, I'm going to be using various node wrangler hotkeys to quickly link things up, like Shift-Alt left-click automatically links up the geometry of whatever you're clicking on to the output, regardless of what that is. So if you see me just clicking on things and things hooking up, those are all going to be node wrangler hotkeys. So of course, geometry nodes lets you do tons of different things, like instancing, or you can generate other meshes and output those instead, or use them to do things to your main mesh. But most of what we're going to be doing is simply taking a mesh we're inputting and getting some information about it, mainly the normal, and then outputting it to the shader. We've got the same material on all these objects, and I've got that hiding on my other monitor, which I will bring over when the time is right. And for now, that's just showing us the normals in the shader, so it has nothing to do with this. So even though I've plugged normals into an output, it's not hooked up to anything. So we have to get this sending information to the shader, and then on the shader end, we have to get it inputting the normals from the geometry nodes, not just from the geometry node, the regular one. So there's a ton to know about geometry nodes, and I'm not going to try to cover all of it in this video, of course. We're just going to focus on getting our normals from this input node into the right format, outputted properly into our shader on the model, and behaving the way we're used to our custom normals behaving. And that means stuff like Autosmooth, edge split, sharp, etc. And that will be quite enough for one video. The main thing we're going to be talking about is Blender's Mesh Data Attribute System. We're all familiar with the idea that you have a mesh and it has various data layers on it. In our object properties, we've got UV maps and vertex groups, vertex colors, all this stuff, and attributes. And actually, all of these are mesh attributes of a sort. We've also seen some of these attributes before in previous videos when we went into the data API, but there is an easier way to look at things. In geometry nodes, we can pull up a whole spreadsheet over here. And this is showing all sorts of information about the evaluated mesh, which means whatever geometry is plugged into the group output. If I unplug this, then nothing is showing up. And we can also change it to a viewer node, and we can add a viewer node. I'm going to use Control-Shift to automatically add one. And then it lets us grab whatever data is plugged into the viewer node, much like we're used to in the compositor. So here we can look at everything that is on the mesh, and it's broken down by mesh element type. We've got vertices, edges, faces, face corners. If we had curves or point clouds, etc., there'd be more to show up, but we can see that there's 0 next to all of these. And what we're looking at here is our stuff here. So for example, if we go to our cube, which is a bit simpler, we can see we have all 8 of our vertices by index, and it has their position, and then it also has their value in our vertex group called split. And we can go in here, and if we turn all this stuff on, it's pretty easy to see. There's vertex index 1, and it's red, so it has a weight of 1, and we can see that's going on right here. So this is a convenient way to view the attribute data and elements of our meshes. On complex meshes, it can get pretty crazy. Like, here's the head, and it has all sorts of stuff because it has a lot more vertices, and then, of course, this is from a fully rigged mesh, so it has each vertex's value in every single group on the mesh. So that's a lot. And then for edges, it's actually simple because the only edge attribute is crease. For faces, we've got shade smooth, material index, and normal, our favorite. And for face corners, we've got the 2 UV maps I have on there. So a lot of what we'll be doing with geometry nodes is inputting attributes and doing various things with them, and then perhaps also outputting and changing them. And if you think about it, that's what we're used to with most modifiers, Pretty much every modifier you want to use is going to have things like a vertex group input. Well, that's an attribute input. So it's not really anything we're not used to. We access attributes in our nodes by 2 methods. Some will have an input node like normal. These are on the input menu, which is divided into 2 things. This is generic properties like a value node like we're used to in shader nodes. Or here are things that actually input mesh data, like normal, position, radius. And not everything is here. Like, where's the UV map input, for example? We know our mesh has UV maps, it's right here, and we can see it in our face corner data, so how do we get it? We have to set it up as a group input. So to do that, we can go to group input and add another one. The plus symbol copies the one you have selected, so that's going to be geometry. But I'll change it to the right type, which is vector for UVs. And we can set, the name and tooltip or whatever, but we don't really care about that right now. And we can see that it's been added in the input section of the modifier. So all we've done so far is define the type of data that will come in through this socket, this input, which is a vector, 3 numbers, X, Y, and Z. And here we can actually just set those. If we plug this into the viewer, you can see every single element in the mesh is getting whatever values I happen to stick in here. So if we actually want to tell this to use our UV map, we click this button, and now it gives us a field where we can select any of the attributes on our mesh. It will let us select any type we want. We've got face, edge, point, different domains, those are called, of attributes, and also different types. Float is a number between 0 and 1, a boolean is true, false, a vector is 3 floats, integer is a number without a decimal, etc. So there's our UV map, so we can select that and see our UV data. But we could also select like a vertex group, like this split one, so that's the wrong thing, that's just a single float. And it looks like it's just all zeros, but actually if we scroll down a bit, we can see it is there on the mesh. It's just that that single float value will go into all 3 of our vector channels, unless we change this, to a float. So you can mismatch the data types, and it doesn't necessarily matter. Well, it matters when it matters, but it doesn't break or give you an error or not put anything through. It just does its best to convert one vector type to the other, just as if you were in the node editor and you plugged a float into a vector socket. It's exactly the same. So we'll select the UV map we actually want, but keep in mind that this is filling a group input. So on these other objects, we haven't told it to use that UV map as the input. And if we, try to select a UV map with them, what's going to show up here is all their stuff, and it's not necessarily going to be the same UV maps. So that means we can have our UV socket, but on different objects with the same geometry nodes modifier on it, we can tell it that we can put different data into that UV. And that can be useful, but it also means that sometimes, if you want all of your objects to input the same UV map of the same name, then you don't have a convenient way to do that. You have to manually set it up on all of them. But that's actually changing in 3.2. I'm using 3.1 for this video. But yeah, it's going to change soon, and by the time you're watching that, you may be able to go over, and there are going to be attribute input nodes, either here or here, that let you choose an attribute by name. But for now, we'll have to do it this way. So that's how we input things. Now, how about outputting them? We've made an output on the group, and we've plugged something into it, and that isn't doing anything, because we haven't assigned it to output to an attribute here on the modifier. So again, when we click on this, we see the list of what's available on our mesh, and what you'll notice is that there is no normals option. There wasn't any normals option on the inputs either, so that's not really surprising. The things we can choose in this field are the things that exist in our object data here. Basically, things that you can make here. Things that are like intrinsic parts of the mesh and we access through nodes here, you can't output this way. Now, some of these you can set. For example, we can come over here to geometry and there is a set position. And on our inputs, there is a position. So we can do something like run our geometry through the set position and then offset it, or we can plug the position node in and then do things to that, like grab a vector math and, well, now we're adding to it for the same effect, or we could scale it, or whatever, and that's all great stuff for transforming your geometry. So is there a set normal node? There is not. In fact, we have very few sets at the moment in geometry nodes. This is because geometry nodes does not really support the whole custom normal system yet. So far on these meshes, we're used to working with the Autosmooth, which creates a custom normal layer on geometry data. If you add a modifier like a normal edit or whatever, and you apply it, then this data is down here, custom split normals data. So when we clear that, now we've deleted it. So geometry nodes has no access to this at all. The normals it's taking in through this input node are just the face normals, and there is no way to set a custom normal or to interact with them. If we want to send our normals out, it needs to be as a generic attribute, which would mean something that will show up in this list. So let's go make that. We can come over here to our attribute section and just make a new attribute with the plus symbol. we get to set the name, which I'll do GeoNormals, and we choose the domain, which is the type of element it will be on. In this case, we want face corner, and we'll get to why, and the data type. And again, if you're not familiar with all of these, you can look them up. I'll be putting the documentation for Geometry Nodes link in the description, but it's a vector. So we make that, and this is now a generic attribute that doesn't have anything in it. We can now see our GeoNormals in our outputs, and now that we've selected that there, whatever we plug in here in our normal socket is going to go and be written to that attribute. So if we, say, made an input of that attribute and selected it here too, then we can view that with our view node and we see it's totally empty. If we plug our normal node in and we go ahead, I'm going to duplicate this and apply the duplicate, then now there is data in our Gen attribute because we wrote our normals into it by applying the node. And actually, while the node is live, it's technically overwriting whatever's in them with this normal node. So if we made another geometry nodes tree as a separate modifier after this one, and had that input GeoNormals, like, I think we could just duplicate this. Let's delete and recreate GeoNormals to clear it. And now on our second copy of the node tree, we can see that there is data in it. On our first copy of the node tree, there isn't. So it's dynamically, like, live writing the normals into it at the moment. So now we are actually writing to a data layer on our mesh, which means we can go get them in our shaders. So we'll pull up the shader editor here, and currently we are outputting the regular mesh normals, which we don't want. What we want is an attribute node, which lets us input any attribute. So we type in the name, and it's a vector, so we'll grab that. And there they are. They're only there on Suzanne because we haven't assigned it in the modifiers for the other ones. So I've already set up GeoNormals on these. If it was named something different, we could be assigning the normals to output to something different, but this attribute node in our shader is bringing in GeoNormals, so we'd have to have a second attribute, bring it in by the different name, and then combine them. So it's simplest if you just have everything have standardized naming conventions. So there's our normals, right? Done? Well, let's compare to the real mesh normals. Get a mixed node, we can flip between the two, and already we're having problems. First of all, the ears are a bit weird because when I did that thing earlier of applying that normal edit modifier and then showing clearing the normals, after you clear the normals, it doesn't necessarily recalculate them correctly. So let's do a recalculate outside. That fixes the ears. Because while Geometry Nodes is not reading in custom normals, you can still have flipped normals because it's just getting the normal info from the face. So we've cleaned that up. And now everything's fine? Not quite. It's hard to see, but there is some very tiny difference. Let's do a trick to make it easier to see what that difference is. Instead of mix, let's go to difference. And that's kind of hard to look at because we're looking at the difference between two vectors of 3 colors. So instead of a difference node, a mix RGB difference, let's use a different one. I'm going to grant us a vector math and set it to distance. And this is also giving us the difference between two things, but only as a float. And that's because this is getting the distance between these two vectors as if they were proximity, even though normals are a rotation direction, not proximity, but it still works. This is telling us the difference. So where it is black, there is no difference, and where it's white, there's a bigger difference. So now we can really see what the problems are, or at least where they are. If we turn on some subsurf, we can see that the distances get smaller, but also we can kind of spot that they're not at the edges of faces, they're kind of on the interior of faces. It does look kind of weird, and they're happening where the topology is weirder, like that triangle fan there. So what exactly are we looking at? Well, it's pretty difficult to explain, but let me show you the solution. We're going to copy that distance node and get ourselves a normalize. And now the problem is solved, except for a tiny bit of sampling at the edges, which is mostly a render thing. Black means no difference. So now our attribute normals are behaving just the same as our real normals. But what is a normalize and why did that work? Well, to answer that, we're going to have to go back to some things that we passed over, but actually matter quite a bit. We'll leave just our attribute node plugged in and switch back to our spreadsheet. So whatever we plug into this output socket is just going to come in into our shader now. So if we wanted to do, say, a color, we can just do that. Or we can just scrub these and set whatever we want, because even though we have called it normal and used that word a bunch, it is just a generic attribute. It is literally just 3 numbers. That's all it knows. But actually, there's a little bit more because we have these output settings here. It's not just that it's 3 numbers, but it's 3 numbers set to attribute domain point and being output through a attribute that is face corners type. So let's talk about what those mean. As we mentioned before, our normal starts out as a face normal. It doesn't show up under vertex or edge or face corners. It is face type. And we've talked about the difference between face and vertex normals in the previous video. So the thing coming out of this normal node is just the face normals. And if we set our attribute domain on the output to face and plug that in, we have flat shading. Well, we have face normals, true normal. The same thing as if we render normally and had set this to shade flat. So converting to point gives us smooth shading, and that's because smooth shading is vertex normals that have interpolated the face normal. You may remember in the overview video, we talked about how this works. The normal of a vertex is the face normals of all the faces that it's part of averaged. And that's how you get smooth shading. That's the whole linear interpolation thing we've talked about. So when our face normals go through this output, they are converted to point data, and part of that conversion is doing the interpolation. And that's true of anything we send to point data. If we're outputting as face corners, then it's still the same flat shading because there's no interpolation step. It hasn't had the data converted to vertex data. It's converted to face corners, which is a conversion, it just happens to end up looking the same. And if we convert to edge, it is now edge data, which is doing whatever this is. Some stuff has kind of been interpolated. I can see some gradients, but I think it's gone like vertex to edge. It's more complicated. But anyway, this isn't really useful for anything, so we don't really need to worry about it. Group outputs are not the only place that these implicit conversions take place. Geometry Nodes is full of implicit conversions because pretty much every node expects certain inputs and gives certain outputs. And it's not always obvious what. You just kind of have to know what the nodes are. For example, on the split edges node, which we'll be working with soon, it takes geometry and it takes a selection. The selection is a Boolean value. It's either selected or not, true or false. And the type is edges because it's deciding whether to split edges. So if you were to plug in a float value on edges, then it would be converting from float to Boolean. And if you plugged in a float value on faces, it would convert from float to Boolean and from face to edge. So understanding the rules for how it converts these domains is pretty important. We can observe some of these conversions directly by using the viewer node. So we're looking at normals, which are face data. And when we're on face, we can see that the value from the viewer and from the normal is the same. But if we switch to vertices, now the value in the viewer has changed, because now it's telling us the value of the normal per vertex, which is interpolated. And also for edges, it's different. And for face corners, it's not different because face corners can hold the same data. It's not interpolating anything. Then there are other nodes that don't change anything. For example, if we get just a vector math node, then it's not converting the data at all. Like we plug that in, I mean, we're just adding some amount. It's adding to the face data still. But things can get interesting if we start adding things together that are different types. So position is vertex data. So if we add vertex data and face data, then what are we getting exactly? And it's actually kind of hard to see, but it's got both flat values for the face data and it's got a bit of a gradient for position. You can see it pretty clearly there. And that is because we are still on face corners here. If I change this to face, then it's going to have taken the position and converted it to a flat value for the face. I believe the position of the face is the average of the vertices that compose it. And, if we go to point, then now it's interpolated the face data, and, you get what you expect. So we have to stay aware of these things. Generally, we're going to want to take proper control over our interpolation, especially when we get to implementing split normals. So we're going to leave our output type as face corner, and that's also the type we're using for the whole attribute. We could change the attribute type, and it wouldn't really matter. We could change this to just face, and it would still let us put interpolated data through. But we'll leave it as face corners because that matters for geometry nodes that might input it. But it wouldn't matter for sending it to the shader specifically. The proper way to control our conversions is the capture attribute node. This lets us capture any generic, aka anonymous attribute. They get called both. So we set it to vector, and we take in whatever vector we want, and we've got it set on point. And now we have our smooth shading back. Because this was faces, it got captured as point, so now it's been converted, and then it's output as face corners. So the reason we want this set up is because face corners can hold both interpolated and non-interpolated data. Whereas if this output is set on point, then everything is going to get interpolated or reinterpolated once it outputs. So we need this if we want to be able to split edges, which we will in a little bit. So let's get back to this Normalize node. I said we needed to talk about this to understand that, and what we've come to understand is that we're handling our own interpolation in the geometry nodes. We're doing our own conversion from face to vertex normals. And actually, we are doing our own everything for the whole normals pipeline. There's a pipeline that goes from having the mesh, getting its face normals, converting its vertex normals, and doing various other things to it before it shows up in the shader. The normal that comes out of the geometry node in the shader, not to be confused with geometry nodes, is the output of that whole pipeline. It also involves things like Autosmooth and sharp edges and stuff like that, which is what we'll be creating with edge split later. And that pipeline outputs a normalized normal. Normalization is something that will come up constantly when we're doing vector math with normals, and we'll be doing a lot of that in future videos. So this is the first time we're really encountering it, so we're going to go on a little bit of a tangent and explain it. Normalization can refer to a lot of different things in vector math overall. It means you've normalized it to something. And that can be all sorts of different things. But in the case of Blender and 3D vector math in general, when you say normalize, it means normalized to have a vector length equal to 1, which is what this node does. It takes in whatever vector and it sets it so that its length equals 1. In the case of a shader, it's per pixel. If you use this in geometry nodes, you'd be doing it per face or vertex or whatever domain you're feeding into it. So that just raises the new question of what is a vector length? And, that's something that we can find here. We can look at the length of a vector, and we have math to deal with that. But what is that? Well, to answer that, we need to go all the way back to what is a vector in the first place and what is it actually representing. So I've got some examples that will help us understand that. Here we have a plane. It's only got one face, so this should be pretty easy. We can see its normal in our spreadsheet, -1. So facing down the y-axis. If we rotate it, we can see that the normal is changing. So here we have an empty object, and let's set its location to be what we see on that normal. So x is 0, y is -0.574, and z is 0.819. And if we take a look at that, let's go into edit mode on this face, and we're going to turn on normals. And we're going to set the size of that to be 1. And it is pointing exactly at our empty. If we move the face around, nothing changes because the normal is rotation, not position. When a vector is just holding a position, then the xyz is just the position in space, like that's a vector. But when a vector is telling us rotation, what the number means is the angle is between 0 and if you had an object at the xyz position of the normal. The length of a vector is the difference between 0 and the xyz position. So we can see here we set our normals to display as 1 long. If we set them shorter or longer, it still passes through that point. So you could have a different value expressing the same direction. But the reason the length is important is for having math be consistent when you're working on rotations. If we rotate our face around, we can see that the largest numbers we ever get are 1. Well, 1 or -1, largest and smallest. The range is 1. And that's because, well, 0 represents no rotation, -1 represents 90 degrees rotated this way, and 1 represents 90 degrees rotated that way. And we start off with, we flatten that. We've got 0 on y right now. So as we rotate around x, that's a 90-degree rotation, and that's -90 degrees. So most vector math that is used for rotation and direction stuff works under the assumption that 1 and -1 are the largest to smallest values, and that they correspond to 90 and -90 on that axis. So if you have numbers bigger or smaller, things can start to get weird. It doesn't matter for some, it does for others. We'll run into examples later on when we get into normal mapping and all that stuff. But that's the basic concept. If your length isn't 1, then the math stops working right. So if your length isn't 1, you need to normalize to get it there. Let's look at that in action. So I've set the empty to 0, and I've brought the empty object into our geometry nodes with object info, and we're looking at its location, both output to our colors and through the viewer node. So as I move this object around, we can see that we're getting its vector here, and things are changing color on the plane. So we'll fly that around a bit, and it's picking up the xyz of the position. Now let's get the length instead. Length is just one number, and it's effectively the distance between 0 and the position of the empty. So we do also have a distance node, and distance to 0 is the same thing as length. And we can see that changing our color, and once we go 1 or higher above, it's just pure white on the plane. Now let's add a normalize before the length. And the length is 1. No matter where we put it, the length is going to be 1. And if we get rid of the length node entirely, we can see that, the normal is changing, but always the length is going to be standardized to 1. If you're curious about how the actual math in these nodes works, you can just Google any of this. Just Google length of a vector or calculate length. Magnitude is the same thing as length in most cases, so you can look for either of those. Basically, it's the Pythagorean theorem. So you get the position, you get 0, and say you have a triangle between those, then the length is the hypotenuse of the triangle. So that's going to be, a squared plus b squared equals c squared. Then when it's in 3 dimensions, there's another element to that, and it gets more complicated. But this is fairly basic math stuff. You could build the length out of math nodes if you want, but we've got it here, so we don't really need to worry about any of that. Normalize is a bit easier to do mathematically. It's just the original vector divided by the length, and that will always get the length to be 1. So these are the same thing. That's nice and simple. So the normalize node is less needed, but still nice to have for convenience. Although when you're doing this, you can run into some trouble if your length is 0, because then you're dividing by 0. Blender does handle that automatically. In most cases, if you're trying to divide by 0, it just gives you 0. But in situations where it doesn't handle that automatically, that can create some problems for you. So now we understand normalization and vector lengths, and we're moving towards understanding our problem. To help us keep doing that, we need to compare our incorrect normals with the correct base normals. And to help us do that, I've made an instanced group of our 3 objects. So this is a single object, and its geometry nodes are bringing in the collection holding these 3 as instances, and then realizing them, which means making them into a new mesh and not counting as an instanced object anymore. And the reason for that is so in the shader, they have the same material, but I can give them different object indices. And what that is over here in object, you can set a pass index. So that's got 0, and this has 1. And that means if I plug in, we look at our object info and render, we have 1 for our real object and 0 for the second. And we can use that to mix between our original normals and our geometry nodes normals, which looks like this. And now, as I turn that off, we can see it's going to be changing one but not the other. Actually, to make this even easier, we'll have a mix between normalized and not normalized. So now we can toggle on and off without recompiling. Now, the difference between the 2 normals is really small. It's really difficult to see. And if we put a subsurf on, it's even smaller, which actually tells us something, which we'll understand in a minute. So what if we look at it with shading? Like, how much of a difference is this really making to our shading? Like, is this even worth spending time to solve? It's not even making any difference to our shading at all. That's weird. Well, that's because we're turning a normalize on and off, and our shader, diffuse shading, automatically involves normalizing the incoming normal. All shaders normalize their incoming normals. To which you might say, like, okay, well, why do we need to do this then? Well, the answer is because if we want to do any other math based on these normals before it hits a shader, it's going to be wrong until we've normalized it. So that's why we're doing this. And we can make it quite easy to see, which is by doing my favorite thing of absolute and step on normals. And now when we turn the normalize on and off, you really notice it. In fact, what we're looking at, it kind of looks like we're missing curvature. So before we had looked at the distance between our real normal and our geometry nodes version, but now let's take a look at the length. And we can see that there's a very slight distance. It's hard to see, so I've got a compare node. This is just comparing to 1. Is it 1 or not? And we can see when normalized, everything's white, so everything is length of 1. And when we go down, large amounts of the mesh are not length 1. So I'm showing you these various normals troubleshooting tools because this is what I went through when I was trying to figure out what my problem was. When I first started doing geometry nodes normals and I didn't know why they were different. I figured out the solution was to normalize them pretty fast, but I didn't really understand why until I looked at this and I could see that, well, it looked like this was less curved. We were missing curvature. And then I figured out that this must be some sort of interpolation problem because everything is interpolation problems. And for our next example, I will visually show you exactly what is going on. So I've thrown together a geometry nodes setup that will help show what's going on. It looks like this. This is a mess. I'm not going to explain how all of it works, but I will leave it in the file if anybody is really curious. But it's a mess and it's quick and dirty, so I wouldn't really use it as an example of anything. So the core of it is this cylinder cutout, which is similar to stuff we looked at in our earlier interpolation examples. If I render it, we've got normals on it, so we can see they are being interpolated around it. And I've got it set up with a subsurf so we can see different amounts of cuts. We'll just look at it from the side for now. So I'm going to turn these on. These are some lines pointing from the vertex normals, and they are 1 unit long. Exactly 1 unit long. And here are planes that are aligned with the vertex normals. And if I set these, they are now displaced by an amount equal to their length, which is 1 unit long. We can see they match the lines. So that's great. What we're going to do now is subdivide this. And it's not subdivide smooth. It's just a regular subdivide. So it's adding more cuts, but it's not curving anything. It's not like the subsurf modifier. And what is happening under the hood of this setup is it is taking the original normals before the subdivision and transferring them to a subdivided version. And what that means is that we're getting the linear interpolation of these normals from the original shape. So this is simulating what we have in the shader when we have our 2 original vertices here and here, and then anything between is a linear mix. And what we can see is that we still have our length of 1, but then the plane that has been offset from the vertex normal by the length of that vertex normal's vector is not 1 unit long. In other words, our original shape, which didn't have all these cuts, when that is transferred to the new shape, which does have all of the cuts, what we're getting at any point between this original vertex and this original vertex is some mix between the two, and somewhere in that mixing process, it is losing some of the length of the vector. It is losing some of the curvature. And that kind of makes sense if you think about it, because the simpler shape here, the smooth normals, are simulating a curve that is, it's not actually an octagon. It's simulating a curve around here. So what we're seeing here is basically the difference in vector length between where the surface actually is and where it should have been if it was actually a curved surface. We can see that even more clearly if we go back, and I'm going to just turn up the resolution of the original. And notice the more I turn this up, the closer it gets to being an actual circle, the less the deviation in length is. It's a bit hard to see, but there's way less of a problem. And then if instead we go down, then it gets way, way worse. So this is basically what is happening on the pixel level in the shader instead of on the extra vertex level. And of course, if we come over here and enable this normalize, problem solved. It has fixed the length. And that is exactly what we were doing in our shader. And if we render this, we can do it in the material here too and see it happening. So that normalizes on, now off, now on, now off. So there's the change. Okay, back to our main objects for the last bit we need for the shader. I'm going to pull this out of the collection and hide it because we don't need to look at it. So on these two objects, I have added a mask modifier that is going to hide some of the faces so we can look at the back faces of the mesh. We're looking inside it. So everything looks the same on the front, but when we're looking at the back face, things are different. Or perhaps I should say that on our geometry nodes normals, both sides are pointing in the same direction, which isn't good. You know, this face is supposed to be pointing this way, and currently it thinks the back face is also pointing that way instead of this way. So that's no good. Whereas on the real normals, it's proper. This is pointing the opposite direction. The back faces of the normals need to be inverted. And that can't be done in geometry nodes at all right now. I think geometry nodes doesn't have a concept of a back face. I might be wrong, maybe we can do it there. But it is very easy to do in the shader. So that finishes up our shader, and I've made a node group that I have stuck all of this into. And this will be in the file. So there we go. Better fix that. We've got our normalize, we have our invert, and that's it. That's all we need for this. You just plug your attribute in there. So now we can move on to the next task, which is getting edge split set up. So we've got our smooth shading working, but now what about Autosmooth? Autosmooth does two things. Well, it does one thing, but it does it to two different things. It splits edges. It splits edges based on this angle and based on anything that we mark sharp. That will get split regardless of angle. Now you probably won't need these sharp split edges for a character's face, which is the main focus of this series, but you do need them for pretty much anything else, and you might need them for some character faces. But either way, the things we need to learn to set this up are things we'll use for the rest of the setup. Now, I keep saying split edges, and that's a very literal term, because what Autosmooth is doing is mimicking if these edges were split from each other, and thus not getting any smooth interpolation. If we grab a edge split modifier and set it to the same angles, it's going to do exactly the same thing. Like I've got these edges marked sharp, so it's using those, and I'll turn it off and turn the Autosmooth back on, same thing. And in fact, I think the way this works is in the GPU when it's rendering it, what the sharp is doing is telling it to split the edge there. So pretty much everything gets split out in the GPU and for one reason or another. So of course, we're not going to use the edge split modifier itself, because then we're left with the split edges, or we have to like re-merge them. We're going to do the edge splitting in the geometry nodes graph. We'll start off with replicating sharp edges. So I've set the Autosmooth angle to 180, and I've marked a bunch of edges on both models, and then we've got this one here for reference. We've got our nodes. We're going to want to do the split before we capture the normal. So we will get a mesh split edges node, and that split all the edges, so that's returned us to flat shading. And while we're here, to make it a bit easier to see what edges are split, I have a displace node group, and that looks like this on the inside if you want to make it yourself. So we'll drop that in there, and we'll need to set it to a small amount. We want it to be just enough to see if there's a gap between those edges without having to render the normals. All right, we'll move the rest of this away for now. So it should just be a matter now of getting our sharp edges and plugging them into the split edge node selection. It's a Boolean edge input. So we'll make an input for that. And sharp is not in the list. Maybe it's an input? No. So this is one of those things that I mentioned earlier where it's a property we want, but we just don't actually have it. Geometry Nodes has not implemented it yet. But by the time you're watching this, maybe they will have. The developers are talking about it. I think they have some tasks open. So hopefully you'll just have it within a version or two. But for now, we're going to have to fake it by another method. So how else do we get an attribute on the correct edges? Well, crease exists. That's already there by default. And we can just toss that in here, and it split the edge. I've got these two creased. And that's all well and fine, unless we actually need it to do its job of controlling subsurf. If we're not using it, then we can disable it on the modifier, or if we wanted this cube to stay flat, we could just not subsurf smooth it. And yeah, if you're not using crease, you can use it for this instead, but chances are good you're going to want it to work. So we need something else. Another option is to set up our own new generic attribute that will be the right edge data. And as I said before, there's not really any way to directly create an attribute unless you use a Python script. But what we can do is use crease as a shortcut. So I'll come and select all my sharp edges and crease them. And now I will input crease. And we're going to send that to an output. Make sure it's on there as well. And on both these objects, we'll make a new generic attribute. It can be called sharp, it's edge, and it's a Boolean. We'll do that on both. And then in the node tree, we'll just send this straight to the output and make sure we've selected that. Doesn't matter that this is still called selection. And then on both of them, we'll just duplicate and apply the node group. And now, instead, we'll change it over to use that sharp as the input. And that's working. Oh, right, gotta turn the group back on. All right, so that totally works. And now we could undo those creases and put things back to how they were before. So there's nothing wrong with this method. It gets us the correct results, but it is a bit finicky to do because we have to repeat that process anytime we want to change which edges are marked. And if we're using creases for other purposes on the mesh, then we will have messed up all our creases every time we do that. So that's not the final method we're going to go with for now because it's not ideal. We're going to use vertex groups instead. So I have created those. I've got a group called split, which has those vertices in it. And same thing on this mesh, which I will set to not show the geometry nodes in edit mode. There we go. Same stuff selected. And in the node graph, I will change the input to a float, which we don't really have to do, but call it sharp group. And set that to be, I call the vertex group split, and then I call the input sharp group, but you know, you get the idea. And that is splitting edges, but currently we can see it is splitting too many. It's not just splitting the ones that we had sharp before, it's splitting all edges attached to the vertices in that group. We can fix this problem by doing a domain conversion, like we talked about earlier. So right now, we have a vertex group, which is point domain and type float, and it's going into a edge domain type Boolean. And the way it's interpreting it is the edges that are being selected is any edge that has a point in the vertex group, an edge being defined by 2 points. So if either of the edges' points are in the vertex group, it's counting it. What we want is to only count edges where both their vertices are in the vertex group. So we'll grab a capture attribute, and we'll set the type to Boolean. Plug that in. Now we've converted it to a point Boolean, and the problem is solved. Now, we actually have a handy bit of reference for how this works. Here is Blender's reference manual, and in the attribute, in the geometry nodes attribute reference, it actually has a list of the behavior when converting Boolean domains. So we can see here we are doing a point to edge. Edge is selected if both its vertices were selected. So we get this behavior from the capture attribute, but it won't do this behavior automatically just from going into a Boolean socket on the split edge. It's not doing the same conversion implicitly there as we get from the capture attribute node. So this is much more convenient because we can just control the edges that get split with a vertex group. And we don't have to go through that whole rigmarole of rewriting a new sharp attribute. There is one drawback, though, which is we are going from point to edge. So if we look in edit mode, we can see that if we just select our sharp edges, we don't have, say, this edge here selected. But as soon as I go into vertexes, now it's selected. And that's because both the vertices that make it up are selected. And we can see that that edge is getting split. It's a bit hard to see the displace. So this edge would not have been split by sharp, but it is being split because we're going through a vertex group and we have that implicit conversion. So that is the downside of this method. That won't always matter. It depends. If that matters, you can do the other method, but most of the time that probably won't matter. So this is fine. And there's another problem waiting to pounce on us. Let's turn on Subsurf. Tons of stuff is split. What's going on here? You might recognize this from weight painting. If we go in here, we're looking at our split group, and as we turn the subsurf off, we can see we're getting a gradient from 1 to 0. And with it on, even though there's new points here and actually the edge is split, it still goes 1 to 0.5 to 0. We can also see what's happening if we use the viewer node. With subsurf off, the value of the vertex group is either 0 or 1. Then we turn it on and we get a ton more points, and we can see we also have some 0.5s in there, like on index number 9. And if we look at the Boolean, that is true. So what's happening is when subsurf adds new geometry, the value of the new vertices in any vertex group are a mix between the values of the two vertices it's between. So 0 or 1, this ends up with a value of 0.5. And then when we capture the attribute, it's considering any value above 0 to be true. So those 0.5s are all becoming extra edges that get split. So we need to tell it to not do that. We can't change the logic of the capture attribute node, but we can eliminate any values below 1. So instead of it being greater than 0, we're going to make it equals 1. For this, we're going to use a utility node called compare, and we're comparing a float, and we need equals mode. And we're comparing to 1, not 0. And we can leave it with a very small epsilon. An epsilon is 1 plus or minus the epsilon. So a little bit of that can help. If you set it to 0, you can have problems with floating point accuracy. But we can see now that it is working. We are back to the previous behavior, and that holds even if we go to higher levels of subsurf. If we go to like super high levels where the difference between the values in the group is less than the epsilon, then we'll start having problems again. But I don't think we could. I think the program will crash before I can go that high. So problem solved. So that's our sharp equivalent split group done. I'm going to stick this over here for now and grab a new input, and we will make the angle-based edge split next. So this time we're going to be replicating the edge split node, where if the edge in this input is below the angle between the two faces, then that edge gets split. So to start with, we're going to need another input, which can also be a float, and we'll call this split angle. And I'm going to set that to have a minimum of 0, max of 180, because that's how the modifier works. I guess it can default to 70 because that's also how Autosmooth works. And that's what we'll put in there. Now, our work here is actually pretty easy because we have a node that just gets us the angle between two faces. It's called edge angle. And let's see what this is giving us with a viewer node. We've got unsigned and signed angle. We're looking at the cube, and we can see on edges that the value coming out is 1.571. We know all of these edges are 90 degrees because it's a cube. So why is it 1.571? Well, that's easy. Because it is in radians, and that is equal to 90 degrees in radians. But our input is going to be in degrees because that's more user-friendly. So we'll need a math and 2 degrees. And now 90. And what is signed and unsigned? If I plug that in, it's all the same thing. But let's go over to Suzanne, and sometimes it takes a moment to update. And now if we plug in signed, we can see that some of these values are negative, and unsigned, they are positive. So that's what the difference is. Signed means it counts negative. Unsigned means it only just shows you the angle. And so that's the same as absolute value. So we do want the unsigned in this case because we don't care which direction the edges are angled. And now we will compare that to our incoming split angle. And we'll use the compare node again. This time it'll be set to less than. And we're seeing right now everything is true. And as we adjust the angle, as we get above 90, they all flip to false. So now let's plug that in there. And it's working on the cube. If we set it to exactly 90, it's not split. And for the edge split, if we set it to exactly 90, it's also not split. As soon as we go below 89.9, it splits. And similarly here, as soon as we go down, it splits. So that's working. Let's get rid of this displace. We've got our normals back. I'm going to set both of these to 70, just as an arbitrary number. And let's compare them to our others. This is using Autosmooth, and we'll set that to 70 as well. That's looking the same to me, but just to be careful, we'll grab our shader, and we'll check them there. We'll use our distance node, and no difference. Wonderful. With subsurf, still no difference, so it is working. Back to the geometry nodes, we do still have the slight problem that our edges are still split, which we don't really want. There could still be a problem hiding in the comparison that we can't see because, of course, we were comparing the distance to this mesh's Autosmooth normals, and those are also getting affected by the edge split. So we need to have our mesh not be split. There are ways we could recombine the edges, but then who knows what that will do to our data, and that can cause tons of problems because when you merge points, it messes up index order. And index order matters a lot. So what we really want is to not have to do that. And the easiest solution is to take the original geometry again and just transfer back the normals from the split version. And for that, we need a transfer attribute node. We'll send the original to the output, put that on vector, index, and face corners. And that actually does not go there. Note that the input on the transfer node is source. So this is the source of what we're transferring, and the destination is this geometry. We'll get into this in more detail in the next video, which will be more about transferring things. But basically, the destination is implicit. And that is because geometry nodes resolves the node graph kind of working backwards for some bits. So it's going to be looking at this geometry and then getting this transfer. It's saying there's an attribute. Where does this come from? It comes from a transfer. It comes from here. So source, destination. So if you start here and work backwards, then it makes sense. If you're looking here and you're thinking, well, this should have a source and a destination, then it doesn't make sense. And there is our split normals on the right object. And they are coming from this transfer, and our mesh is no longer split. So what we've done here is we've transferred a vector on index, which is mesh element index, aka topology mode, like we're used to. And there's our nearest face interpolated that we're also used to. And we did it as face corners, which is also what we're used to from the data transfer modifier. You may recall from the previous videos that face corners are independent of the vertices and edges. So even if we split edges, which duplicates and adds vertices, as long as the face count doesn't change, we can do a topology transfer on face corners. So that's what we're doing here. We effectively have duplicated the mesh, done all of our splitting, got the normals, and then transferred the normals back to our original unsplit mesh. We've got our distance back. Everything is set to 91 split angles on both the modifier and on Autosmooth. And we can see the only discrepancy is that extra selected edge on Suzanne. So everything else is correct. And now I have set everything to 70, and it's exactly the same, which means it's all working. And subsurf. Yep, we are in business. Our setup is complete. Okay, we almost made it to the end. I put all the setups together to show a comparison, and I've tidied up the nodes, but even at the last second, disaster can strike. Something is different. Let's look at our distance. There it is. What's wrong? We've got subsurf on. If we turn subsurf off, then the problem is gone, although something on the Suzanne is unhappy now. So what is this? There's one little node I forgot to put in, and it is because of subsurf. If we zoom in, we have our limit surface option. If we turn that off, the problem goes away. So what is this doing and why does it matter? Well, this is simulating the surface and making a very slight change to how the subsurface behaves. And because of that, and I think a floating point error, which is where when you have a bunch of decimal points and a number is really tiny, it can start to get confused. It's thinking that the angle here is very slightly different than it is. So if we go and we change our split angle by even a tiny bit, now they're the same. And we need to do the same thing on the group, and now the problem is gone. So even just that 0.01, actually we might be able to go as low as 0.001. Yep, that's enough. So that's the floating point precision. Now we don't want to actually have to set that extra fraction of a degree in our setups. So instead we will solve it in the nodes. Over here, let's grab another math node and we'll just add 0.001. And it's still going to show up as different because we can't add 0.001 to the Autosmooth, but it doesn't matter. We know that it is actually fixed here. So now it's the same. And doing that actually also fixed the slight difference on Suzanne, because that is also a floating point error. So, problem solved. So this time we are finished for real. There's our nice shading. There's our nice normals. And this is the file and setup that I will put out on Gumroad for free. But of course, if you have enjoyed this content, you are welcome to leave a donation or support me on Patreon. In the next video, we'll be going deeper into geometry nodes and doing some actual transferring and transfer setups. So, thanks for watching, and I'll see you in the next video.